Now, last time we were looking at our problem where we were doing the model of the defibrillator and trying to calculate the voltages and currents. And as we saw before, we had 7 unknowns, but only 6 linearly independent equations we could use to solve. And as I pointed out last time, if a circuit has n nodes, we can only get n minus 1 linearly independent equations, assuming that these are based strictly on what's available through KCL. So, how do we get around this problem? We need the third law we'll need for this semester, Kirchhoff's voltage law. Or, as we will abbreviate it during this class, KVL. How do we apply KVL? Well, let's look at this circuit. Before I actually start writing down what KVL is, we need a definition. So let me erase some of this stuff and let's look at a definition that's relevant. All right. So in order to apply KVL, we need a definition for a loop. A loop. What is a loop in circuit analysis? Specific meaning. A loop is any circuit path that can be traced starting at any point in the circuit so we can just pick any arbitrary node in the circuit, any starting point we want, and then it can be traced through one or more circuit elements. In addition, it must return to its starting point without passing through any other intermediate node more than once. So that's a bit of a mouthful here, but really what we're saying here is very straightforward. Pick any point, trace a path, come back to the starting point without going through any point once, or any point more than once, any intermediate point. So looking at this, clearly, and hopefully everybody sees this, by inspection, there's a single path in this circuit. Now granted, I may go clockwise or counterclockwise, but it's still the same path. So, we have one loop in this circuit, and given this definition of a loop, we can now do the definition of Kirchhoff's voltage law. KVL says that the algebraic sum of all the voltages around any loop must equal 0. So that's basically the formal definition for KVL, but just as with KCL, there's kind of a different definition, a more simple definition I like. Let's write that one down. Around any loop, the sum of all the voltage drops must be equal to the sum of all the voltage rises. So drops and rises. Remember we talked about this before, a voltage drop and a voltage rise. And at that time I told you, once you became more familiar with circuit analysis, you'd start to see this again. It would become kind of implicit, kind of obvious. So let's consider what we mean by this. Let's look at this alternate form for KVL. And let's see how we can apply this concept. And before I write a KVL equation for this circuit, let's go back to our simple battery model that we looked at before. So here we have our battery example where we had the short-circuited battery, which was composed of a voltage source of 1.5 volts and a resistor of 1.5 volts. And as we talked about before, since these two wires are the same node, the same connection, I've got the same 1.5 volts all the way across. And so I've got the same voltage across the resistor as I do across the voltage source. Okay, but if you look at this, obviously, this is a circuit with two nodes. Let's label those A and B. Okay? So, let's start at node A, and I'm going to arbitrarily choose a direction, clockwise, counterclockwise. It doesn't matter. So I'm going to start at A, and I'm going to go clockwise. Okay? Well, if I go clockwise, I have a drop of 1.5 volts. And then I keep going around the circuit through node B, and then I rise, go from negative to positive 0.5 volts. 1.5 is equal to 1.5. So the rise and the drop are equal. Kind of obvious, but what you can see here is very simple idea here. Now I can start at node B and go counterclockwise. Okay? If I go counterclockwise, then I rise through 1.5 volts, and then I drop positive to negative through 1.5 volts. And again, around that loop, I get that 1.5 is equal to 1.5. So it doesn't matter whether I start at A or B, whether I go clockwise or counterclockwise, I get exactly the same answer. 1.5 is equal to 1.5. So this is KVL in a very simple sort of trivial form. So given this idea of starting anywhere and going either direction, let's do the same thing here. Let's pick any arbitrary node and then go either clockwise or counterclockwise. So let's start with node A again. And let's go clockwise with this circuit. All right? So if I'm going clockwise, let's look at the polarities of the voltages as I travel around. Okay, so going A, going clockwise, negative to positive, VD is a rise. Then I continue around through node B, and then across the voltage across that resistor, VL is a drop, positive to negative. Keep continuing around. Now another drop, V1. And then keep traveling around, and then I've got VS, negative to positive, that's a rise. And there's my KVL equation. The drops must be equal to the rises. And I simply write my equal sign and add the terms on either side. Now, here I started at A and I went clockwise. You say, okay, Dr. Holman, what if I started someplace else? Okay. In this case, let's start at D, node D. Let's go counterclockwise. If I start at node D and go counterclockwise, then in this case, V1 is a rise. Continuing around, VL is a rise. Keep going around, VD is a drop. VS is a drop. So notice, in this case, the rises and the drops flipped around because the direction changed. I either went clockwise or I went counterclockwise, and then what I defined as a rise or a drop got switched around. But notice, this equation and this equation are the same equation. So it doesn't matter where you start, whether you go clockwise or counterclockwise, as long as the drops are equal to the rises, you'll get the correct equation. Okay? So, that's my equation. No matter where I start, I get the same one. There's really only one KVL equation here. So here's my result, and in this case, of course, I actually know what VS is. VS is just 1,000, so I'm just going to replace that. So there is my expression for my KVL equation. And now, what else do I need? I now need my KCL and Ohm's law that I wrote before. So there's my Ohm's law, and then finally my KCL. And remember, I had 4 KCL equations, but only 3 linearly independent equations, so I just picked 3 of those. Don't worry about the 4th one because it doesn't add anything. But now, what do I have here? I have 7 equations. 1, 2, 3, 4, 5, 6, 7 to go with my 7 unknowns, which means I can now solve. So if I solve, I'll get the following. IL will be equal to 197.94 milliamps, which will also be equal to IS and also be equal to I1. ID is equal to minus 197.94 milliamps. VD is equal to minus 9.897 volts. V1 is equal to 0.396 volts. And VL is equal to 989.707 volts. All right, something I want to emphasize, very important to everybody in the class. Notice, here are the equations, and then I give you the answer. Exactly. This is not a math course. It's an applied math course. I don't need to see how you went from here to here. In fact, you're being given a really powerful tool, Mathematica, in order to go from this point to this point. So you don't need to show me all the intermediate steps. All I really need to see is your equations, put them into Mathematica, and then get the answer. That's all that's really required. So Mathematica, you want to become very conversant in it. Now granted, there are calculators that can solve simultaneous equations, but I don't think any of them come close to Mathematica or MATLAB for that matter in terms of just being able to type the equations in and just get your answer. So I strongly recommend to everybody, become conversant in Mathematica. Practice. Don't wait until the night before a quiz or an exam to try to figure out how to use it. You should be working and doing homework problems and learning how to use this tool. It will save you an enormous amount of effort, and it gets rid of a lot of the work of having to solve. So you really want to focus on getting the correct equations. You don't want to focus on the mechanics of solving those equations. No point to it. Now another nice thing about Mathematica is Mathematica doesn't care about dependent equations. So Mathematica will ignore linearly dependent equations. So remember, we threw out one of those equations out of the KCL because I said they were linearly dependent. If you had left that fourth equation in, it wouldn't have made a bit of difference. As long as your dependent equation is consistent with the rest, Mathematica will still solve. So you don't have to sit here and think about, okay, which equation do I take out, or are all of these dependent? Do I need to test that? Just type all the equations in and then solve. That's really the way to work these. All right? Now, one last thing we want to do, let's check and see if we got the right answer. Let's go and let's do that by applying the passive sign convention. Let's apply the passive sign convention to do what we would call a power check. If we've solved this problem correctly, the sum of the powers must be equal to 0. Okay, let's do that. So P1 for the R1 resistor will be equal to V1 times I1, and that will be equal to 0.078 watts. PD will be equal to VD times ID is equal to 1.96 watts. PL is equal to VL times IL is equal to 195.90 watts. Now resistors automatically follow the passive sign convention because we defined the voltages and currents to follow them. When you're solving a circuit, sources don't need to follow the passive sign convention while we're solving because we don't know whether the current coming out of the source is positive or negative in advance. So PSC doesn't apply. It's not a resistor. But if I ask you to calculate the power, you have to use the PSC. So now I want to know, what is the power of that source? Well, I can't use it in this case because IS is coming out of the positive terminal. But I can absolutely flip it around and say minus IS. Now the current's entering the positive terminal, which means that the power of that voltage source will be equal to Vs times minus Is, which will be equal to minus 197.94 watts. And you know, if you add all of those together, you get 0 watts. So in other words, the sum of the powers must be equal to 0. Check. I know I got the right answer because I got the correct power balance. So this will always work. Works now, it will work all the way to the end of this course. You will find that If you perform the power balance, you'll get the right answer. Now, it's not the only way to check an answer. There are others. I'll show you some of those. But it is one that is certainly very reliable, although it can be tedious. Now, one last thing I want to say about this before we leave this example behind. Remember, this was a defibrillator which was being used to zap a patient. And as we said before, this RL resistor is the resistance of the patient's body and heart. Now notice, the power of that resistor, PL, is 195.9 watts, which means that this is 195.90 joules per second. A watt is also a joule per second, energy per unit time. Which means in half a second, this patient's body will absorb 97.95 joules. And why did I point this out? Well, this comes down to something you've seen before, but maybe you never questioned. You ever watched a TV show or a movie where they're restarting a patient's heart with a defibrillator? You hear them yell a number. 100, okay, clear, patient jumps. Doesn't work. 150, clear, boom, patient jumps. 200, clear, boom, patient's heart gets restarted. What are those numbers they're yelling? They're not yelling the joules of energy they're pumping into the patient. That's what they're doing. So they're increasing the amount of energy to try to get the heart to restart. And what you do is you have a very high voltage that you deliver in a very short amount of time, so you have a very precisely measured amount of energy that gets into the patient's heart. You want to bring them back to life. You don't want to cook them. Okay? So that's our first circuit problem. And we've kind of gone through everything. We applied Ohm's law, KCL, KVL, defined nodes, defined loops, solved the circuit, and then went and checked the power balance. All right? So, given all that, next time we'll actually work another example. We're going to put all this together into a more interesting and more complex circuit.